Section 4.2, Limits and Continuity. Now that we know what a function of more than one variable looks like and how to graph them, we can start to do calculus on them. So we'll start with limits and continuity. Before we get into the mathematical notation of a limit for a multivariable function, let's talk about a few elements that we need to understand. First, if we're looking at the limit of a multivariable function, then we're really talking about maybe a limit of a surface if our function has two input variables. So on the screen we see the 3D surface, which looks like the top half of a cone. That's the function that we are thinking about the limit of. Another thing is that the limit has to allow some domain point to approach a specific point. So I have the point C, that's in the xy plane. That is what we are going to allow our input to approach for this limit. So let's consider some domain point that's not exactly at the yellow point C. So I've got a white point on the screen. It's in the domain, I can tell, because it's in the xy plane, and I want to allow it to approach the point C. So I'm going to let it move around, and it's kind of moving around at random here. And that's important to understand, is that this point can really travel any path it wants so long as it ends up at C. So that's the first thing that we're going to start with, is that we're considering some point that's not C in the domain, and we're going to watch how the output of the function changes as that point moves. The output of the function comes from plugging that white point, the coordinates of the white point, into the function, and then plotting that in 3D. We can see that the point on the surface is directly above the point in the domain. And again, we can watch the point move around, and we can see how the function output is changing based on where we are in the domain. So our goal is to watch the function output as we are moving towards the point C. I'm going to click and drag this here. I can move that point however I want, and I can see that as I move the point in the domain, the function output is changing. Here it's 2.41. Now it's 2.52, and as I'm getting closer to C, I can see that the number is going beyond 3. And then finally, when I'm right on top of C, I can see my function output is 3.61. Another thing we'll talk a bit about is paths on the surface. So as we're allowing a domain point to approach the point C, we're watching what happens to our function, the surface, the outputs. So notice that as I'm moving through the domain here, I'm creating a path on my surface as I'm traveling to the point C. So we're calling this a path on the surface, and it's just all of the function outputs that came from the domain point that we were moving towards C. A limit for a multivariable function is a little bit similar to what you've seen in Calc 1. To prove that a limit exists, we would need to use a Delta-Epsilon proof, which basically says that the distance between a domain point and the point that we're approaching, so this is our domain point, we're just calling that a generic xy, and then the point that we're approaching in our limit is the point C. So again, we're trying to show that the distance between the domain point, notice the x and the y here, and the point we're approaching, notice the A and the B, we're looking at the distance between those 2 points. And we're saying that we want to make that distance between those 2 points very small. And we're expressing that by saying that we're stuck between 0 and a number delta. And the reason why we need it to be very small is because if we find the right delta, usually it's very small, then we can say that the distance between our function and this limiting value is infinitely small as well. Now the L in this notation is what we're saying that the limit is equal to. So if we're talking about the limit where a domain point approaches the point AB for a function of x and y called f, and if we think that the limit is equal to L, then we should be able to do a proof that says for every epsilon you can think of, there exists a delta that will make the distance between the points infinitely small. Now, the visual for this is a little bit complicated, but if you can relate it back to the concepts in Calc 1, that's pretty helpful. So in Calc 1, we looked at a rectangle that represents delta and a rectangle that represents epsilon. In Calc 3, we can't just use 2D rectangles because we're working in a 3D world. So we're trying to narrow in on what we're going to call a neighborhood. So any point around the point AB is in a neighborhood. We call that a delta neighborhood. And then we're going to squeeze the function value between 2 planes rather than within a rectangle. You will learn more about these details if you go on to study real analysis or complex analysis. For now, I just want you to understand that it's very similar to Calc 1 and understand what the visual looks like. The other part that I want you to understand is that proving a limit exists is more complicated than simply computing a limit. There's a difference here. To prove a limit exists, first of all, you would have to have a guess at what the limit is. Now that's a little tricky because if you want to prove that a limit exists, what I'm telling you is first you have to know what the limit is. So say you have a good guess. For example, for this function that I'm looking at, for xy squared divided by x squared plus y squared, for that function, I'm assuming that the limit is L, as a domain point approaches the point 0, 0, so we're approaching the origin. I have to first have a guess for what L is to be able to prove whether or not this is true. This is not a way to compute a limit, it's a way to prove that it's either true or false. The proof of this is pretty complicated. I'm going to show you a very watered down version of it just so you get the idea. And the reason why I want you to get the idea is because I don't want you to mistakenly think that you're proving a limit exists. We're not going to prove that limits exist in this class. So you should never get confused and think that you are proving that a limit exists, but just in case, let me show you what you would have to do if you wanted to make that claim that you proved a limit exists. First, we would start with that statement that we think the limit of our function is equal to 0. And then we're going to use the 2 ideas that came from the definition of our delta-epsilon limit, which says that we need infinitely small distance between our function and the limiting value, as well as an infinitely small distance between our domain point and the point we're approaching. Now notice here that the point we're approaching is 0, 0, so the distance from our domain point to the origin is just the square root of x squared plus y squared. To prove that this limit exists, the first thing that we're going to do is start with this notation, the absolute value of f minus L, where I plug in what the function is and what L is. So I've plugged in f of xy, and I've plugged in L. And then we're going to do as much algebra as we can to simplify the expression we have on the left. Now we have absolute value bars, and we're writing minus 0. So there's quite a bit that can be cleaned up here. First, we don't need to write minus 0. Second, we don't need to take the absolute value of positive 4. It's already positive. Y squared, also already positive. And same with the entire denominator. So I'm going to reduce that absolute value to only apply to the factor of x in the numerator, because that's the only thing that could possibly be negative that the absolute value would turn into a positive. Now from here, we're going to have to do some really creative mathematics to get to the delta that we need. Now, I've got the lines written out here, and I'm going to walk you through each of the steps. So starting on the left, that is the simplified version of the expression we started with. And then we're going to make substitutions so that we can move down the line going right. Now the first substitution is coming from the fact that we have 4 times the absolute value of x times what I have written really large down here. That factor, y squared over x squared plus y squared, it's always less than or equal to 1. And that's because the x squared term in the denominator means at the very least we're dividing y squared by y squared. But when x is not equal to 0, we're dividing y squared by a number that's larger than y squared. So we can make this replacement where we pull out the y squared over x squared plus y squared, and we replace it with 1, as long as we use the appropriate inequality. Notice that I'm not putting an equal sign between these things. They're not equal. We need to use the inequality that comes from the substitution we just made. So now we're looking at 4 times the absolute value of x. But remember that the absolute value of x can also be rewritten as the square root of x squared. And if you're thinking, why in the world would I make that change? Well, it's because our goal is to get something that looked like the second statement from our definition. So hold on, we'll get there. In this case, we're making a substitution that's exactly equal. So we're taking out the absolute value of x, and we're going to replace that with the square root of x squared. And so we're going to put an equal sign between those two expressions. Then we come to our last substitution. Not really a substitution, actually we're just squeezing another number inside of our square root. So if we started with 4 times the square root of x squared, but we add a y squared inside of the square root, then of course our number is going to get bigger because we're adding a positive number. The reason why we do that is because this looks like the second part of our definition for delta epsilon. Remember, that's the distance between the domain point and the point that we're approaching. Because we see that in this line of inequalities and equalities, we're going to pull out that expression and replace it with delta using the appropriate inequality symbol. So now we're at a point where the function that we started with, remember that was f minus L in absolute value bars, it turned into this simplified version, and then we did a few replacements until we got to 4 times delta. And our goal was to take that f minus L expression and show that there exists a delta that makes this true. Now we've worked ourselves down to the point where we now have f minus L absolute value is less than 4 delta, and now we need to make it true that that's less than epsilon. So we look at these last two steps and we say, what delta should we pick to make this true? Well, if we let 4 delta be less than epsilon, and we solve for delta, then it says let delta be less than, epsilon divided by 4. So if we use this substitution, then we can make that last step. So if we have the absolute value of f minus L is less than 4 delta, but I tell you that we want delta to be less than epsilon over 4, then my 4's divide off, and I'm left with just epsilon. So we get exactly what we wanted. The absolute value of F minus L is less than epsilon. If that felt like it made your head spin, I don't blame you. It takes a lot of practice for this to make sense and to be able to go through step by step really smoothly. The great news for you is that I'm not going to make you do that in this class. You will see it again in real analysis, complex analysis, but for this class, I just want you to understand what it looks like to prove that a limit exists, as well as what it looks like to visualize a limit for a function of two variables.